Welcome to the Deep Edge. For the last 2 years, the AI infrastructure story has been dominated by one word: GPUs. Who has them? Who can get them? Who can power them? And who can build the biggest clusters? But the industry has quietly crossed a major line. We are moving from the compute wars to the interconnect bottleneck. And that shift changes everything, because as AI models get larger, the real constraint is no longer just how fast a single chip can think. The constraint is how fast tens of thousands, or eventually hundreds of thousands, of chips can talk to each other. That is the new AI infrastructure reality. A GPU by itself is powerful, but an AI factory is not one GPU. It is a massive synchronized system of GPUs, CPUs, memory, storage, switches, optics, and software all working together. And when one part of that system slows down, the whole training job can stall. This is the bottleneck we need to solve. So today, I want to talk about a part of the AI build-out that does not get enough attention: optical networking. Because compute may get the headlines, but optical is becoming the foundation that determines how far AI infrastructure can actually scale. Let's break it down. Segment 1, why copper ran out of road. Let's start with the physics. Modern AI training jobs are tightly synchronized. The GPUs are not just running independently, they are constantly exchanging data, gradients, parameters, checkpoints, and intermediate results. That means the network is not just moving traffic in the background. The network is part of the compute system itself. And this is where tail latency becomes a major issue. If one link is slow, if one path is congested, if one part of the fabric cannot keep up, the entire cluster can wait. And when that happens, expensive GPUs sit idle. That is not just a performance problem, that is an economic problem. For years, data centers relied on copper. Copper was familiar, copper was simple, copper was cost effective, but copper has a hard physical ceiling. As data rates push toward 1.6 terabits, copper signals degrade very quickly. Passive copper may only be useful across 1 or 2 meters. That is fine inside a rack, but it does not work when you are trying to wire a large-scale AI data center with tens of thousands of GPUs. You simply cannot build a 100,000 GPU AI cluster on passive copper alone. The reach is too short, the signal integrity is too difficult, and the power penalty becomes too high. That brings us to the second issue: energy. In AI infrastructure, power is everything. Power determines how many GPUs you can deploy, how much cooling you need, and whether the data center can scale at all. A large share of networking energy is spent simply moving data, not computing it, moving it. And the interconnect itself can account for a meaningful portion of total draw. That is why the shift from electrons to photons matters. Electrical interconnects consume 15 to 25 picojoules per bit. Silicon photonics can reduce that to the range of 5 to 8. And with in-package optical I/O, that number can fall even lower, less than 5 picojoules per bit. That changes the architecture, because every watt you save in the network is a watt you can use somewhere else. More GPUs, more memory, more useful AI work. In other words, optical is about system economics. Segment 2, the optical toolkit. So what does it look like? It is not one technology. It is a stack of technologies moving at the same time. The first piece is high-speed pluggable optics. Today, 800 gig optics are becoming the baseline, but the industry is already moving quickly toward 1.6 terabit optics. That matters because AI clusters are hungry for east-west bandwidth. The traffic is moving across the data center, rack to rack. But pluggable optics also come with a challenge. They consume power, they generate heat, and at very high speeds, the path becomes hard to manage. That brings us to the second piece of the toolkit: Linear Pluggable Optics, or LPO. Traditional transceivers use DSPs to recover the signal. DSPs are powerful, but they add power, cost, and latency. LPO removes the DSP and allows the switch chip to drive the optics directly. The goal is simple: lower power, lower latency, lower cost, and less complexity. For AI clusters, LPO is a very important step. Then comes the bigger architectural shift: co-packaged optics. This is where things get really interesting. In a traditional switch, the optical module sits on the front panel. At high speeds, the electrical signal travel becomes expensive. CPO changes the model. Instead of the front panel, CPO moves the optical engine much closer, sometimes onto the same package as the ASIC. That collapses the electrical distance. You reduce power, improve signal quality, and open the door to much higher bandwidth density. This is why CPO matters for AI. It is not just a packaging innovation, it is a scaling innovation. It helps AI move beyond electrical traces. The economics can be meaningful. CPO delivers major improvements in efficiency and reliability, freeing up power capacity for the cluster itself. There is also another important technology, optical printed circuit boards. Optical waveguides replace electrical paths with light. Think of it as moving light deeper into the system, from the cable to the board and eventually closer to the chip. That is the direction AI infrastructure is moving. The network is becoming optical from the outside in. Segment 3, optical circuit switching. Because optical is not only changing the physical interconnect, it is also changing the switching architecture. This brings us to OCS. Today, traffic moves through electrical packet switches. Light is converted to an electrical signal, processed and converted back. That is called optical conversion. It works, but it burns power, adds latency, and creates scaling pressure. These mirrors steer beams of light from one fiber to another. No packet processing, no OEO conversion, just light being switched as light. These mirrors steer beams of light from one fiber to another. No packet processing, no OEO conversion, just light being switched as light. The benefit is significant. Latency can be dramatically lower, power consumption can be lower, and the system can be speed agnostic because it steers light rather than processing packets. OCS is speed agnostic, supporting 400 gig, 800 gig, or 1.6T signals effortlessly. In AI training, communication happens in phases. OCS allows the network to be dynamically reconfigured to match the specific workload. The network can sometimes be reconfigured around the workload. You can create optical paths that match the specific training phase. This opens the door to flatter, more efficient designs. OCS gives the AI factory a faster way to move massive amounts of data. Now let's bring this back to economics. Segment 4, the economics of light. This is where the optical story becomes strategic. For 2 years, the industry thought AI was just about who buys the most GPUs. But that view is incomplete. A GPU waiting on data is stranded capital. A GPU blocked by network congestion is underutilized capital. It's an economic failure. This is why optical interconnects matter so much. They determine how large the cluster can become and how efficiently they communicate. They determine how much power the network consumes and whether the data center can support the next generation of AI workloads. And they determine how much of the expensive silicon actually performs useful work. That is the shift. Efficiency of the system. AI infrastructure is no longer just about raw compute. It is about the efficiency of the entire system. The GPU matters, but it's only one part. The real question is this: can the entire system keep the GPUs fed? Can it move data fast enough, synchronize jobs efficiently? Can it avoid tail latency, reduce power per bit? Can it scale without collapsing under its own complexity? That is where optical is critical. Can it avoid tail latency, reduce power per bit? Can it scale without collapsing under its own complexity? That is where optical is critical. AI workloads are pushing the physical limits. Copper cannot scale, and electrical interconnects consume too much power. Traditional architectures add too much latency. Optical changes the math. It gives AI infrastructure more reach, bandwidth, and efficiency, and it provides a more scalable foundation for the next generation of AI systems. Closing takeaway. Interconnect is the key. So here's the takeaway. We have spent the last 2 years assuming that AI infrastructure is mostly a GPU race. But the next phase will be defined by something deeper, interconnect, because GPUs do not train models in isolation. They train models as part of a system. And the larger the model, the more important that system becomes. Optical allows it to scale. It allows massive clusters to act less like a collection of machines and more like a single unified AI factory. Compute gets the headlines, but light holds the AI factory together. And in the next wave, the winners will be the companies with the best efficiency, those who connect GPUs with the lowest latency and highest bandwidth. That is the real AI advantage. It's not just an upgrade, it is becoming the real AI bottleneck. Thanks for listening to The Deep Edge. I'm Mota, and I'll see you on the next episode.